Hi Mindsetters, welcome to Spring School, and this is Maths Paper 2 live show. We're going to be working through exam paper questions from the exemplar. I'm here, unusual to see me on this side, but we've had a little bit of a change around. I'm joined today with Natasha. Natasha, good morning.
Hi, John. Well, great to see you, John. Always a treat. Thank you for joining us, Mindsetters. And as John said, today we're looking at paper 2 questions coming from the 2014 Maths Exemplar. Specifically, we're going to work through selected examination questions that will cover analytical geometry, Euclidean geometry, trigonometry, and statistics. So quite a lot to cover, John.
Yeah, absolutely. And guys, you can get your notes and they have the solutions as well. So you can follow along as Natasha is going through them. The links are on the page. They're about to go onto the Facebook page, facebook.com/learnextra, or you can visit our website, which is learn.mindset.co.za, and just follow the link through revision. Learn Extra Revision, Learn Extra, and then Learn Extra Revision. Even on the main page, you'll see Spring School. Go to the updated schedule and download the notes from the little box there. Guys, I hope you've got lots of questions. Natasha and I are eager to hear from you, so please post them onto the page, and we'll take as many as we can. But I think let's get into that first question right now. Thanks, Natasha.
All right, guys, so question 1, we're going to start, as we said before, from the 2014 Exemplar, paper 2. This specifically is adapted from question 4, and this is our question 1 for today, dealing with analytical geometry. So let's go through the question firstly. They say, in the diagram below, the equation of the circle having center M, okay, so on your diagram, that's the point M, they tell you that the equation is x plus 1 squared plus y plus 1 squared is equal to 9. Obviously, when you look at that straight away, you analyze and you see that you can work out the center of the circle and the radius immediately from that given information. They tell you that R is a point on chord AB such that MR bisects AB. All right, so we've got. Now, guys, the thing that looks a little bit confusing here is there's no circles drawn in. You can superimpose, you can draw in your own circle on this diagram. But let's look at what this information is saying to you. There's a chord AB. R is the midpoint of this chord AB. I will draw in a circle a little bit later on as we go through the question. And ABT, so your straight line, ABT is a tangent to the other circle with center N being 3 and 2, and it's tangential at the point T 4 minus 1. So in other words, this tangent ABT just touches the circle center N at point T. And what I'm going to do is let's put that little circle in, just so that we have an idea of what is going on. And as I said, as we go through the question, I'll add in our bigger circle a little bit later on, and we'll take it from there. All right, my circle looking a bit oblong at the moment, but you'll get the idea. There we go. All right, so that's what we need for now. Let's go to the first question. It says, write down the coordinates of M. Now remember, in the beginning, I'd said to you they'd given you a lot of information because they gave you the equation with circle center M. They've given you the equation of that circle. So therefore, remember it's given to you in the form x minus a squared plus y minus b squared is equal to r squared. So it's given to you in standard form, which means you can read your center straight from there. Your center would be A and B. All right? Just remember, very importantly, your signs. If we've got x plus 1 squared, that means x is equal to negative 1 would be the x part of the coordinate for the center of the circle. And if y plus 1 is the other y minus b part of your equation, well, y is equal to negative 1 will be the y coordinate of the center. So part 1, our coordinates of the center, minus 1, easy marks straight from the given information. All right, next part, determine the equation of AT in the form y is equal to mx plus c. Now, obviously, it's important for you to take in all the information they give to you in the actual question, right? They stated something very important about line AT. They told you that that's a tangent to the circle with center N, all right? Which means if that's a tangent, we can make a few deductions. Okay, so let's go back to our diagram. And I'm going to try and make my circle a little more circular if I can.
Tasha, it's difficult on that board.
Is
It's
it?
the board that has the aspect ratio is not quite right.
Okay.
But I think you're
As
doing
long
okay.
as we've got the idea.
Yeah, I got the idea.
As long as we've got the idea. We want it to be a tangent. So remember, tangent only touching at one point. So let's move it a little bit up there. Okay. So we have line ABT being a tangent to the circle with center N. Okay. Straight away, that should get you guys thinking about your theorem from geometry. Yes, it's analytical geometry, but you can't forget the geometry that you know as well. We know that the line from the center of the circle is perpendicular to the tangent at the point of contact, radius perpendicular to tangent. Okay? So what that means, since we've got the coordinates of N, which is the center of the circle, and we have the coordinates of T, the point of contact, if NT is perpendicular to ABT, which it is, we know that the product of the gradients, so the product of the gradients of line AT and NT, the product of those gradients would be -1, and the reason for that is we know that angle T is 90 degrees, the radius was perpendicular to the tangent, so therefore the product of the gradients will be -1. So we're going to use coordinate N and T to work out the gradient of line NT, and then use that in order to work out the gradient of line AT. Remember, we want the equation, so we don't stop there. All right. So we've got N is 3 and 2. Okay, so we've got N is the point 3 and 2, and then we had T was 4 and 1. So we work out the gradient of NT. We know our gradient formula, y2 minus y1, all over x2 minus x1. So that's going to give me 1 minus 2, it's -1, all over 4 minus 3, it's +1. So therefore the gradient of NT is -1. The gradient of our radius is -1. Now remember, going back here what I said, the product of the gradients of perpendicular lines is equal to -1. So if the gradient of NT is actually -1, that implies that the gradient of AT must be equal to +1. We divide both sides by -1. -1 divided by -1 gives me +1. So we get our product of the gradients being positive, being -1, and the gradient of AT is equal to 1. Now remember here, they have asked you to find the equation of line AT, so we're not going to stop there. We need a point on the line, which we have. We know that T is 4 and 1. We know the gradient of AT is equal to 1. So in order to find the equation of that straight line, we're going to use our formula. Y minus y1 is equal to gradient times x minus x1, and substitute straight into the formula. So we'll get y minus 1 is equal to the gradient, which is 1 times x minus 4. Okay, simplify that, take everything over that's not a y to the right-hand side, and we get y is equal to x minus 4, timesing this 1 into the bracket. Take your minus 1 over to the right-hand side, it becomes plus 1, and you get y is equal to x minus 3. And what you'll notice is I gave it to them in the form they asked. They wanted y is equal to mx plus c, so make sure that your answer actually coincides and is exactly what they asked you for in the question. That's the form that they wanted you to give your answer in. Okay, so just make sure not to lose silly little marks by not exactly answering the question. Okay, let's move on to part 1.3. All right, now here they start talking about circle M. They tell you that it's further given that MR, which we will go up and have a look at the diagram now, MR is equal to root 10 over 2. They want the length of AB, which remember they told you in the question that was the chord of circle center M. They ask you to leave your answer in simplest surd form. So let's go back up here, and I am going to draw another circle around center M, okay, with chord AB, and this is much better. It looks much more like a circle. So there we go. All right. Now, you've got chord AB. They've told you that MR, okay, which is the radius, they told you that, which is the line from the center of the circle, they told you that that is root 10 over 2. Okay. They also told you importantly that point R bisects the chord AB. So AR is equal to RB. Okay. Straight away, you see, as we combine things, hey, this is not just analytical geometry concepts that you've got to remember. Here we've got to remember a bit of geometry. The line from the center that bisects the chord is also perpendicular to that chord. Line from center, perpendicular to chord, bisects the chord. It works conversely as well. So we know that R is the midpoint. We're going from the center of the circle to point R, right? So therefore R, there, angle R must be 90. MR is perpendicular to AB. Key piece of information that we need. And I'm going to draw in the radius because we're going to need that as well in order to work out the distance of R of AB, and I'll explain to you why. Okay, now if you look at your very colorful triangle MRB, okay, we know that MR is root 10 over 2. Because I've joined point M to B, which gives me my radius MB, and I know from the given information R squared is 9 in circle center M, so therefore R must be equal to the square root of 9, which is 3. Obviously, we're only interested in the positive length because it is an actual distance, an actual length. So therefore, MB is going to be 3. Now, if you work out the length of RB, which it is easy to do now because we know that MR is perpendicular to RB, if you work out the length of RB, since AB is twice the length of RB, we simply take that length RB and times by 2 to get the length of chord AB. All right, so with that explanation, let's get cracking. So I'm going to say, in triangle, and I'm going to do it next to the diagram so you can see what's happening, in triangle MRB, all right, we know, firstly, that MR is perpendicular to AB. And the reason for that, it's the line from center theorem. Okay. So we know that MR is perpendicular to AB. Therefore, we've got a right angle triangle, so I can say, well, MB squared, or BM squared, is equal to RB squared plus MR squared. Okay? So MB squared is equal to RB squared plus MR squared, and that's obviously Pythagoras, given that we've got a 90-degree triangle. Okay, we know that the length of MB we saw before, because it's a radius, that was 3. So I've got 3 squared is equal to RB squared, which is what we're looking for, plus MR squared, MR being root 10 over 2 squared, and that was given to you. So therefore, and I'm getting a bit untidy here, but you just needed the diagram right in your face so that you could see what we were doing. So RB squared is equal to 3 squared minus root 10 over 2 squared. So that's going to give me 9 minus 10 over 4 All right, and that, we can do that in our heads, but we're going to use a calculator because it's right here. So we've got 9. Let's close our smart ink that loves joining us always on a live show especially. So it's 9 minus 10 over 4, and that is equal to 13 over 2. Okay, so this is 13 over 2, and that's RB squared. So therefore RB would be the square root of 13 over 2. All right. So let's see what we've got here. We've got RB is root 13 over 2. So RB, that distance there, is root 13 over 2. If I want the length AB, because R is the midpoint, I simply have to times by 2. So therefore, AB is twice RB. So it's going to be equal to 2 times root 13 over 2. Okay? Now, some of you might be tempted to leave it there, but look, if you look at the question, they say leave your answer in simplest surd form. And if you look at this answer, 2 times root 13 over 2, it doesn't look as simple as it could be. So we need to go a little bit further. We need to take this 2 and put it inside, underneath that square root, so we can leave our answer in simplest surd form. All right? So if we're going to take this 2 and put it into the root sign, what do? We have to square it. All right, remember when you take something out, let's just remind you guys, if I had something like 9 times 2, let's just say 18, inside my square root, we know that that's the same as 9 times 2. So if I was going to simplify this, I would take the square root of 9, which is 3, and put it outside. If I then want to go conversely or inversely and put the 3 back inside the square root, I need to do the inverse of that. I need to square it, so it would be the original answer. Okay, so if I square that, taking it back in, I'm going to get 4 times 13 over 2, and that will simplify. 4 divided by 2 is 2. 2 times 13 is 26. So therefore my answer is the square root of 26. All right,
Natasha,
that's quite a lot to digest.
Yeah, I was just going to say, instead of going on to that distance formula, which I know
Yes.
takes a bit of space and it takes a bit of time, let's go for a break, shall we?
I think that's a very good idea, John. Let's do that.
Okay, guys, don't go away. Make sure you get onto the page and tell your friends about it. And make sure that you're following. If you've got any questions, we're listening to you. We'll take those questions a little later as well. So let's go to a break. Welcome back, guys. We're doing maths this morning, paper 2, and it's all exciting stuff. We're starting with analytical geometry, and we're just about at the end of that question. That was from the exemplar, circles and tangents, really interesting stuff. Guys, if you've got any questions, send them to us. We're on the page. We're tweeting at LearnExtra as well. The Facebook page is facebook.com/LearnExtra. We'd love to hear from you. For now, over to Natasha.
All right, John. Well, with such a great explanation, what do I say? I just go straight into the question. It's all really exciting. As you can see, when I get excited, I get like a mad maths person and I write all over the place. So I'm going to give us a little bit more space on our diagram so we can see what's going on before we answer question 1.4. So I'm going to take off the information that is not going to affect that question at all. All right. So we've got our diagrams clear, and that's what we need. We need our diagrams so that we can make more mess, basically. Okay. So question 1.4 says, calculate the length of MN. All right. If you have a look at MN, that's simply the distance between the two centers of the circles. Remember part 1, we answered the center of circle M was -1, -1. We know what n is. They gave that to us. So therefore, we can simply use the distance formula to work out that length. So m was -1, -1, and n was given as 3, 2. All right. So our distance formula says mn squared is going to be equal to, okay, we're going to start with our x2 first, so it's going to be 3 minus 1 all squared plus 2 minus 1 all squared. Okay, we simplify that. 3 minus 1, so we're going to get 4. 4 squared is going to give me 16, plus 2 minus 1 is 3. 3 squared is 9. 16 plus 9, 25. So if m squared is 25, remember if you're looking for the distance, you need to square root your final answer. So therefore mn would be equal to 5. We're obviously, again, only interested in the positive square root because we are dealing with the distance. So therefore, the length from m to n, the distance between the two centers, that distance there is 5 units. Okay. Let's have a look at part 5. This is the last part of the question, I think. Yes, it is. Okay. So we go back to circle center n, which we've already established, but they say another circle having center n touches is another way to say is a tangent to. Okay, so it's a tangent to the circle having center m at the point K. Determine the equation of the new circle being the circle with center n, and write your answer in a very specific way in the form x squared plus y squared plus cx plus dy plus e. So it's not exactly in standard form. It has been expanded and rewritten. Okay, so let's have a look at the diagram. We've got these two circles. They're touching. Remember, my diagrams are not completely accurate, but they suffice for what we need to establish here. They touch at that point K. Okay? They're asking you for the equation of this circle N. That's the equation that they want. What have you just worked out, guys? Because remember, in maths, often things are linked. We don't do things in isolation. Well, generally not. We've just worked out that mn, your length mn, the distance between the two centers is 5. How is that going to help me to work out the equation of circle center n? Well, we know in order to work out this equation, I need the radius and I need the center. The length of the radius, do we have that? No. Do we have the center? Yes, we do. So all we need is the length of the radius. How do we work that out? Now remember, we've worked out the length of mn. We know that that's 5. We also know that the length of the radius of circle center m, that length there, mk, that is 3 units. And how do we know that? Go back to the given information. They gave you the equation of circle center m. They told you r squared is 9, so therefore your radius is 3. So we know that the length mk is 3, but we've got the whole length mk is 5, so therefore kn, that little bit there, is going to be 5 minus 3, so that's going to be 2. So the radius of circle center n is, the length of that, 2 units. Okay, now we can put that into our circle center AB and work out the equation in the form that they want. So I've got x minus the center of circle n, the x coordinate was 3, and the y coordinate was 2. So it's x minus 3 squared plus y minus 2 squared. Remember to change your signs when you go back and you substitute into your equation. X minus a squared plus y minus b squared is equal to r squared. And we worked out that the length of r was 2, so therefore r squared, 2 squared. Okay, let's simplify all of this so that we can write it in the form they want. We get x squared minus 6x plus 9 plus y squared minus 4y plus 4 is equal to 4. Let's rearrange that. They first want x squared, then they want plus y squared, so it's x squared plus y squared. And then we have the term with the x, so therefore we add anything, any like terms here. We don't have any, so we've just got minus 6x plus dy. So dy is just going to be negative 4y plus e, e being your constant, so therefore we're going to move the radius, that length, over to the left-hand side, and let's add where we can. So we're going to get plus 9 plus 4 minus 4 if I bring the length of the radius over to the left-hand side. 4 minus 4 cancels, and I'm just left with 9. So therefore, in the standard form that they requested, we get x squared plus y squared minus 6x minus 4y plus 9 is equal to 0. And as I said, it's important to answer the question as they want it, and this is the form that they want it in, so don't just times it out or leave it in the standard form. Okay, with that I'm going to cross over to John and see if all of you guys are still following.
It all looks good, Natasha, but I know that the next question is about Euclidean geometry. And I think we need to, even though it's been a short little section, let's take a quick break, and then we can do the whole question for Euclidean geometry.
Great.
So guys, stay with us, don't go too far, and if you've got the notes, go and check out that Euclidean geometry question, work through it, so that when Natasha goes through it, you can check that you've got the right answer. We'll be back right after this. Morning, Mindsetters. Great that you've joined us. We're in the middle of our session, our live session. We're dealing with paper 2. You're not too late to get involved. And we're going to be going on to our next question, which is all about Euclidean geometry. Now, I love Euclidean geometry, and I know you do too, Natasha.
Yes, I do, John. It is actually one of my favorite sections. Mainly because you also get to use lots of colors, and which girl doesn't love color? But also, it's just all about logic, guys, and really, that's what geometry is all about. It's just logic, it makes sense, and if only the world made sense the way geometry does, we would have a good place to live in, John. All right.
I think I agree with you. When everything fits together, it's so wonderful. But guys, you really don't want to get a mental block against geometry. If you learn the basics and learn them really well, you'll be able to solve the problems. Take note of what Natasha's going to do in this question now.
All right, so we're going to get straight into question 2. This one comes from, again, Exemplar, Paper 2, 2014, adapted from question 9. And this is circle geometry. They tell you that in the diagram, M is the center of the circle. Guys, whenever they give you information, especially in geometry, take that information, mark it down on your diagram. And as I said, I used to love geometry. I remember doing it at school, and I loved getting the colors out and making my diagram sheet really colorful, not just for the sake of it, but with all the information that they gave me. So M is the center of the circle, and they tell you that AB is the diameter AB is produced to C. I'm just going to look at that bit of information before I even look at what they want to ask me. Okay, I'm going to look at that information and mark down what I can on my diagram. M is the center of the circle. They tell you that AB is your diameter, all right? So straight away I know, well, if M is the center, that means that AM is equal to MD is equal to MB. And the reason for that, those are all radii. Okay, so already I start thinking like a geometry person, right? We're thinking of all the concepts and all the theory we can get from that information. AB is your diameter, therefore it will produce an angle of 90 degrees in the semicircle, which means that angle D is 90 degrees. We keep that information at the back of our heads as we go on. They tell you that ME is drawn perpendicular to AC. ME is drawn perpendicular to AC. As you can see, that's been marked. Angle M3 is equal to 90 degrees. And it's drawn such that CDE is a tangent to the circle at D. So CDE, that line there, is a tangent to circle center M. When I see a tangent and I see a chord, immediately I start thinking of tan-chord theorem, and I can see on my diagram they've marked angle D4 as X, which I can then use to work out other angles in the diagram. Okay, we're not going to get to that because I know that that is one of the questions. And they say ME and chord AD intersect at F. So MD and chord ME and chord AD intersect at F such that MB is equal to 2 times BC. So, okay, this is what they're saying here. MB, which is this radius here, is twice the length of chord BC. So, if, for example, if we said the length of BC was y, then MB would be 2y. Okay, we just keep that as information that we're going to refer to later on. Okay, now let's have a look at the first question. They say if angle D4 is equal to x, write down with reasons, important, no reasons, half marks. Write down with reasons 2 other angles each equal to x. So we've marked down in our diagram. We know that CDE was a tangent. They told us that. They told you that D4 is equal to x. So following our tan chord theorem, let's have a look. Can we get another angle equal to x? Yes, we can, because we know the angle D4 is the angle between the tangent CDE and chord BD. So therefore, D4 will be equal to the angle A. And the reason for that, tan chord theorem. So I've shown you in the diagram. Let's write the first one down. Angle A is equal to angle D4 is equal to x. Reason, tan chord theorem. Okay, so it makes sense. We have a theorem that backs up our statement. We need another angle that's equal to x, and this is where what we put in already is going to be useful, because we know that M is the center of the circle. Therefore, AM, which we've already marked, is equal to MD, because those are radii. And more importantly, what that gives me is isosceles triangle AMD, and we know that angles opposite equal sides are equal, so therefore angle D2 is going to be equal to angle A, which is also equal to x, and the reason for that is angles opposite equal sides. So angle D2 is equal to angle A is equal to x, and your reason, angles opposite equal sides. Okay, remember to put your reasons in. Very, very important. Okay, so we've done that first part, 2.1. Let's have a look at what 2.2 says. They want you to prove that CM is a tangent at point M. Let's go and have a look at CM. CM, and I'm going to rub off some of the other stuff that I've put on. We'll put it back later on as we need it, but we just need to see what's going on here for now. We've got CM. They want us to prove that that is a tangent to circle through MED. So they're saying if you could draw a circle through MED, then CM would be a tangent. And let's get a little circle in there so that you can have an idea of what they're talking about with those points. So we've got a circle going through MDE. All right. I'm going to make it as accurate as I possibly can. It needs to go through point D. I don't think I'm going to get it exactly going through, but just so that you guys get an idea, you've got a circle going through those points, all right? And you want to prove that CM is a tangent. So what we're going to need to do here is to prove if that were a tangent, converse of the tan chord theorem, it means that M1 would have to then be equal to angle E. So we need to prove that angle M1 is equal to angle E in order to prove that we can draw a tangent CM to circle DEM. All right, now I'm going to diagram my circle, not quite correct, but just so that you guys get an idea of what we are trying to prove there. Okay, so our aim is to prove that M1 is equal to angle E. I'm going to put in the angles that we've already proved in the previous question. A1 was X, D2 was X, and our aim is to try and prove that M1 is equal to angle E. So firstly, our starting point. What is the value of M1? And if you look at your diagram, and I'm going to highlight this nicely so you guys can see, M1 is the exterior angle of triangle MAD. So M1 is the exterior angle of triangle MAD, therefore it's going to be equal to the sum of angle A plus angle D2. Okay, that's our theorem, exterior angle equal to sum of interior opposite of a triangle, so therefore angle M1. So this is part of our proof. We need to state what is the value of M1. M1 is equal to angle A plus angle D2, and that's going to be, since they were both x, it's going to give us 2x. The reason for that, exterior angle of triangle. Exterior angle of triangle. Let's name our triangle. It was MAD. All right. So therefore, we've got M1 is equal to 2x. Our aim is to now prove that angle E is also 2x, because then we can say converse of tan chord theorem, therefore CM would be a tangent to the circle that they want us to prove it's a tangent to. Again, I'm going to erase things so that you guys can see a little bit more clearly what's going on your screen. So again, we've got that's x, we know that that's 2x. All right? We also know we are aiming to look for angle E. Okay? I can see, because remember we've established right in the beginning AB was a diameter, so I can see that angle D, the whole of angle D there, is 90 degrees. Okay, and the reason for that, angles in a semicircle. All right? So that was 90 degrees. I also know that angle D, 3 plus 4, that one down there, that's 90 degrees because, and this one's a little bit trickier to see, the radius, MD, is perpendicular to tangent EDC at the point of contact. So therefore D3 plus D4 interests me quite a bit because that's 90 degrees. That helps me to then get into triangle MED to show that D1 plus D2 is 90 degrees, and the reason for that, also tangent perpendicular to radius. All right. Once I've got D1 and D2, if only I had M2, I'd then be able to work out X. I'd be able to work out E. If you look at angles M1, M2, and M3, those are angles on the same straight line. So therefore, I can work out angle M2 using angles on a straight line. So guys, this is quite a question that you've got to build up. It's not as straightforward as just going straight in and showing this is a tangent that's easily equal to that. We've got to establish and get to that reasoning. So this is what I'm doing. Let's go over it again. I'm going to try and find angle E in triangle MED. Okay, how do I get there? I first established that angle D1 plus D2 is equal to 90, and that's because the radius DM was perpendicular to tangent CDE. I'm now going to find angle M2 and use angles in a triangle to work out angle E. All right, so let's write this down. So angle M2 is going to be equal to 180 degrees minus, remember we're using angles on a straight line, so it's going to be 180 minus the sum of M3 plus M1. Okay, so it's 180 minus M3 plus M1, and your reason for that is supplementary angles, angles on a straight line. Okay, so I know that M3 was 90 degrees. They gave it to you. They told you that EM was perpendicular to AB, so therefore M3 is 90 degrees. And M1, we've proved in the previous explanation, in the previous step, that M1 was equal to 2x. So therefore angle M2, 180 minus 90, is going to give me 90 minus 2x. So M2 is 90 minus 2x. All right, now that I've got M2, I'm going to state angle D1 plus D2 is equal to 90 degrees, and the reason for that, radius perpendicular to tangent. Okay, so now I can say in triangle MDE, angle E is going to be equal to 180 minus the sum of the other two angles in the triangle. Let's go back, reiterate what I've shown you already. Angle E is going to be equal to 180 minus angle D1 plus D2 plus angle M2 because of angles in a triangle. Right, so it's going to be 180 minus M1 plus M2, well, M2, which was 90 minus 2x, plus the other angle, which was 90 degrees, it was D1 plus D2. All right, and what do we get? Hopefully we're getting closer to our answer. 90 plus 90 inside the bracket there gives me 180. And I've got 180 minus 2x within the bracket. So 180 minus 180, the 180s cancel. Minus times a minus is going to give me plus 2x. So therefore, I've got what I needed. Angle E is equal to 2x. All right? So I can say now, angle E is equal to 2x. Initially, I started out trying to show that angle M1 was equal to angle E, and I've got there. Angle M1, we've already shown previously, was equal to 2x as well. So therefore, we've got angle E is equal to 2x is equal to angle M1. Therefore, we can now state what they asked us to prove. Therefore, you now make the statement CM is a tangent at point M. All right, so CM is a tangent to the circle passing through MED. Okay, so therefore CM is a tangent to circle MED, and the reason for that is the converse of the tan chord theorem. So it's converse of tan chord theorem. All right. Okay, so guys, now that's quite a lot of information to take in, and I want to make sure that you guys are following me. You didn't get stuck along the way, so I'm going to quickly check in with John to see if you have any questions so far.
Okay, thanks, Natasha. Do you want to take a little break before we go into the next question?
I think we should. I think we've got 3 more
let's do that. And we'll have a look at the page and see what your questions are. I'm trying to answer some of them as we're going along. And we're going to take a little break. We'll be back straight after this. Welcome back, Mindsetters. You're joining us for Spring School Maths, brought to you by the Department of Basic Education. And we're really so happy that you've had a chance to join us today. Countdown to the final exams is on, and we're into some tough maths that people really sometimes struggle with. We hope that this is helping you. It's not really that tough if you know your work. And of course, if you listen carefully and you follow, let's get on without any further ado and master this Euclidean geometry. Natasha.
All right, thanks, John. So guys, we're continuing with question 2 based on Euclidean geometry. We've answered the first 2 parts of this. We're now looking at part 2.3, where we asked to prove that FMBD is a cyclic quadrilateral. FMBD. Okay? So once again, I'm going to erase what I have on the diagram just so that we can be clear about what we're dealing with. Okay, we've got F, M, B, D. So in other words, they're saying you can draw a circle around those 4 points. Prove that it's a cyclic quad. What are the ways to prove that things are a cyclic quad? How do you prove that any 4-sided quadrilateral is a cyclic quad? That's the first thing you need to think about, because that will tell you what reasoning you need to look for in your diagram. Okay? So the one way you can prove a cyclic quad is to prove that the opposite angles are supplementary, or you can prove angles in the same segment, or you can prove the exterior angle of the cyclic quad is equal to the interior opposite. So you've got three things to choose from, and you've got to look at your diagram and decide what's going to work best for the diagram that you've been given, bearing in mind the information that you've already been given. Okay? So we've already established M is perpendicular, line EM is perpendicular to AB, so therefore angle M1 plus M2 is equal to 90 degrees. Okay, that's angles on a straight line. So straight away I'm thinking that might be a clue of where we need to look, because if I've got angle M and I had angle D, which we do have, because it's angles in a semicircle, we've shown before angle D is 90 degrees. If I have angle M and D, and if they happen to be supplementary, which they are, then I can say that FMBD is a cyclic quad because opposite angles are supplementary. Okay, you could work with B2 and F2, that's going to be much harder to show, so we're going to go with angle M and D in quadrilateral FMBD. So, how do we set it up? I'm going to say in quadrilateral FMBD, angle M1 plus 2. Okay, just go back there and let's have a look that was in fact M1 and 2 and D2 and D3. So angle M1 plus M2 is equal to 90 degrees. Okay, and your reason for there, you can state what was originally given to you in the question. They told you that ME is perpendicular to AC. All right, so ME is perpendicular to AC. That will be our reason there. We then need to state why angle D2 plus D3 is also equal to 90 degrees. And the reason for that was angle in semicircle, or subtended by diameter BD. So angle in semicircle, that's the reason I'm going to use there. So therefore that means, going back to your diagram, D2 plus D3 was equal to 90 degrees because of angles in a semicircle, or you can state subtended by diameter AB. All right. So now we've got our two angles. We can say, therefore, angle M plus angle D, and we restricted that to the quadrilateral FMBD, so we know which angles we're talking about. Angle M plus angle D is equal to 180 degrees. And therefore we can say, therefore, FMBD is a cyclic quad. And your reason for that is since the opposite angles are supplementary. So you just need to prove one pair of opposite angles are supplementary in order for this to work. Okay, one pair of opposite angles supplementary, therefore FMBD is in fact a cyclic quad. Okay. I'm going to move swiftly on to question 2.4 because there is quite a bit to still get through. Question 2.4 states that you need to prove that DC squared is equal to 5 times BC squared. And this is the nice thing about geometry. If they give you information, you're going to end up using it somewhere. You've just got to figure out where. So what information are we going to use here? Something we haven't used as yet. The last bit of information. They told you that MB, which is a radius, is equal to twice the length of BC. Okay? So MB is twice the length of BC. You can, if you like, if you see things easier with variables, you can say let BC equal to y. Therefore, if MB is twice BC, it would be 2y. Okay, if you prefer, you can use variables. There's nothing wrong with that. Just make sure you state what you're doing. So you're going to say let BC equal to y if you decide to use variables. All right. I'm not going to use variables. I'm just going to use it with the letters that are given to us on the diagram. Okay, but you do have that option to simplify this question. Okay. All right, so they're asking us to prove that DC squared, let's have a look where that line is. There we go. That's equal to 5 times BC. Now, as they stand, they don't look like they're related at all. They look like they're just two separate line segments. However, with this bit of information that they included, MB is twice BC, we now get an entire length. We get MC, which is part of triangle MCDM, if I'm trying to work out length DC. We've also established previously that angle D3 plus D4 is 90 degrees because tangent is perpendicular to radius at the point of contact. So I've now got a right angle triangle. Within that triangle, I can work out DC squared using Pythagoras. Okay, so let's go for it. Remember, in what they've asked you to do, there's no MDs and all the rest of it. There's only DCs and BCs, so we want to set up everything to look exactly like that. Only DCs and BCs, no MBs, MD, and all the rest of it. Okay, so I'm going to say, in triangle MCD, MC squared, so this is in triangle MDC, all right? MC squared is equal to MD squared plus DC squared, and your reason for that is Pythagoras. Okay? So, MC squared is equal to MD squared plus DC squared. I'm going to rearrange this so that we get DC on the left-hand side, which is where we want it to be for what we need to prove. So DC squared is going to be equal to MC squared, your radius, minus the shorter side squared. So MC squared minus MD squared. Now we have a problem because we've got MCs and MDs and there's no MC or MD in the question. Okay, so how do we relate it? So this is where we bring in the given information. Firstly, let's start with the MD. How am I going to get rid of MD? Well, I know that MD is equal to MB, and the reason for that, those were radii. All right, we knew that M is the center, so MD is equal to MB because those were radii. So therefore, I can state here on the side, we're going to deal with just MD. MD is equal to MB because these were radii, and that was also given that that was equal to 2 times BC. MB was 2 times BC because that was given to you in the beginning. The reason we're stating that MD is equal to MB is because those were radii. All right. So MD is equal to MB is equal to 2BC, and that's how I'm going to get rid of the MD part of this equation. All right? If we have a look at MC, remember that MB is twice BC, so that's 2 times BC. So the whole length, MC, that's going to be equal to MB, which is 2BC, plus this little length here, which is BC. So MC, the whole length, is equal to 3 times BC. All right, so MC is equal to 3 BC. Let's put that in. So MC is going to be 3 times BC squared minus MD squared, and MD squared we know was 2 times BC squared. So that's going to give me 9 BC squared minus 4 BC squared, which will give me 5 BC squared, which is fantastic because we've now answered the question. So therefore we've got that DC squared is equal to 5 BC squared. All right, and that was all just by using Pythagoras and using the given information from the question. Okay, so pretty straightforward when you get right into how you do it and when you get to the answer, but when you look at it immediately just from what they gave you, it seems like the two lengths weren't even related. So it's important to pay attention to what they've given you. We've got one more question to do on this, which is the similarity question. I'm going to quickly check with John to make sure you guys are all following.
Natasha, it's amazing. The comments are coming in. Guys are really enjoying it. Do you think there's time for it, or do you want a little break?
I think we should finish this off.
Yeah, let's finish it off. Let's go for
finish
it.
this off. Okay, guys. So we're in the mood. We want to get done with this geometry question. Prove, last one, similarity. Prove that triangle DBC, and I'm going to skip now from a yellow pen. Prove that DBC is similar to triangle DFM. Okay, once again, erasing what we've just used so that we can put in the new information. We're trying to prove that, and I've got short-term memory loss, DBC, triangle DBC, there we go. Prove that that one is similar to DFM. DFM, this little one here. Okay, so we've asked to prove similarity. Think about this. What are the ways that you can prove that triangles are similar? Well, obviously it depends on the question, on the information you've been given, which one you will use, but two ways to prove that triangles are similar. Either they give you that the sides are in proportion, and you can use that, or you prove that they are equiangular. And in this case, we're going to work with the equiangular triangles. So if we prove that DBC and FMD are in fact equiangular, then those triangles will be similar. All right, for this we're going to need to add in some of the information we've proved before. We've worked out that D2 was X. Initially, we also worked out, remember in the previous question we showed that FMBD is a cyclic quad. You can draw a circle around those points. So we showed previously that FMBD is a cyclic quad. We are going to use that because I can see that that's going to take me into both triangles. If you have a look at B1, it's an angle in triangle DBC. And then if we have a look at F2, it's an angle in triangle DFM. So therefore, I can relate the two using cyclic quads. B1 is going to be equal to F2, and that's because of exterior angle of cyclic quad. So let's have a look. Let's write all of this down. Okay. So we're going to start with this, and we're going to state our triangles. Remember, it is important to state your triangles and make sure your order is correct. In this case, our order is correct. So we stay in triangle DBC and triangle DFM. First thing we know, B1, angle B1 is equal to angle F2. Angle B1 is equal to angle F2, and it's exterior angle of cyclic quad FMBD. Okay, exterior angle of cyclic quad is equal to interior opposite. So therefore, those two angles are equal. Next point that I can put down is that angle D4 is equal to angle, what was it? D4 we had is equal to angle D2. There we go. So D4 is equal to D2, and we have previously proved that. So we don't need to reprove that. Angle D4 is equal to D2. And they were both equal to X. And once you've got two angles, the last angles by deduction using sum of angles of triangles will just be the remaining angles. They have to be equal to each other. So we're going to say angle C is going to be equal to angle M2. And the reason for that is remaining angle. So angle C is equal to angle M2, and that's remaining angle. Right. So now we can say, therefore, triangle DBC is similar to triangle DFM, and the reason was angle, angle, angle. Okay, so I lied. There's actually one more part to do to this question. They said, hence, determine the value of dm divided by dm divided by fm. We're going to do that straight from the similarity that we've just proved. Okay, you can see it's 2 marks, and as I always say, if you watch our exam revision sessions, let the marks guide you. Do not do half a page of work for 2 marks. We want dm over fm. Remember, because these triangles are similar, you're going to get that the sides are in proportion. We want dm over fm. Have a look at your triangle, your sides that you've just worked out. dm over fm from proportion, that will be equal to dc over bc. And this is just comes from the fact that triangle dbc is similar to triangle DFM. And this is why it's important to get your order correct, because you can then make deductions straight from what you've proved. Okay. So dm over fm is equal to dc over bc. Now, they want a value, which means we can probably go a little bit further with this. So dc and bc, let's see if we know anything about this. dc, well, we've just proved a little bit of information before. Hey, so we're going to use that information from 2.4 to write down what the length of DC is. So DC squared is 5BC squared. We know DC squared is equal to 5BC squared, and this was already proved. Therefore, DC is going to be the square root of 5 times BC, because obviously if you take the square root of BC squared, you just get BC. So now let's put in our ratio. We've got dm over fm. Remember, we said that that's equal to dc, which we can now replace with root 5 bc all over bc. And you can see what's going to happen here. Because we've got BC being exactly the same thing, they cancel out, and we get the ratio dm over fm is just equal to the square root of 5. All right, quite a lot of information. I know you guys need to digest this and maybe ask us a few questions which we can help you with during this quick break, John.
Absolutely. Guys, no more chat. Let's go to that break. Guys, I can't believe how quickly the time's gone, but we're into our last segment, and I don't want to take up too much time because we want to see if we can do as many questions. We've got some questions on trigonometry.
Absolutely.
So, Natasha, let's go.
Okay, guys, so we're going to get straight into the question. This is now a question on 3D trigonometry. It's question 3, adapted from question 7.2 from your DBE 2014 exemplar, paper 2. They say the framework for construction consists of a cyclic quadrilateral PQRS in a horizontal plane. All the information in the question is actually drawn in your diagram. And they tell you it's got a vertical post TP, as shown in the figure. From Q, the angle of elevation to T is y degrees, again, also shown on your figure. PQ is equal to PS is equal to K units. All right. TP is equal to 3 units. And angle SRQ, again, drawn for you, that's equal to 2x. So it's really nice. They've got all the information already put on the diagram. So we can really just go straight into answering part 3.1. Show giving reasons that x is equal to PSQ. So show that angle x is equal to angle PSQ. So really they're saying to you, show that this angle is x degrees. Okay. Remember, in maths, nothing's ever learnt in isolation. We have to often draw from other sections. This now, remember they told you PQRS is a cyclic quad, so this now brings into play the stuff we know about cyclic quads. We know that angle R is given as 2x, therefore opposite angles of a cyclic quad are supplementary, so angle P is going to be 180 minus 2x, and that is opposite angles of cyclic quad. All right, so if this is 180 minus 2x, remember we're trying to prove that this angle S here, PSQ, is actually equal to x. We know that PS is equal to PQ. They gave it to you. So therefore, using sum of angles of a triangle, we can show that angle S is equal to angle Q is equal to x. Let's write that down. So we know that angle P plus angle PSQ plus angle PQS is equal to 180 degrees. We know sum of angles of triangle. Therefore, we're going to have that angle PSQ is going to be 180 degrees, and I'm doing this all in a combination step, and hopefully you guys can follow this. I will go through it again. It's going to be 180 degrees minus 180 minus 2x, which was angle P, and that whole thing divided by 2 because angle PSQ and PQS were equal. All right, so my answer here is going to be 180 minus 180. They cancel out. Minus times a minus, positive 2x divided by 2 is just going to give me x. I went through this but really quickly, guys, because that is algebra, and I want to try and finish this off so that we can get into the meaty part of it. Prove that SQ, line segment SQ, is equal to 2k cos x. Now, you go back to your diagram, and you have a look and see which triangle they're actually forcing you to work with. And yes, they do force you to work with certain triangles because you've got to look at the given information. Okay? So, SQ folds into two different triangles. It's in triangle PSQ and triangle SQR. So, if I'm looking for SQ, I can either find it with SRQ, but I'm not going to be too lucky there because there's no lengths of any sides given. Or I can work with triangle PSQ, which is obviously the one we're going to opt for here. So if I want to work out side SQ, I'm going to do it along here. So in triangle PSQ, I can say that SQ over sine of 180 minus 2x, I'm using the sine rule. So SQ over sine 180 minus 2x is going to be equal to PQ over sine of x. We've just proved that that angle is x. So this is straight application of the sine rule. Okay. And the reason I went for PQ and this triangle is we know that PQ is K. So therefore SQ is going to be equal to PQ, which is K, times, I'm cross multiplying, so I'm going to get times by sine 180 minus 2x all over sine of x. All right, and let's just get a little bit more space here so I can fill that in. So that's going to be equal to, now we can simplify this. Sine of 180 minus 2x, 180 minus is in second quadrant. Therefore, sine is positive there. So my answer here, if I use reduction formula, that's just going to give me k times sine 2x all over sine x. But if you look at your answer, they didn't have any sine x's in there. There was only a cos x. How do we get there? Simple. We just go one more step and we use our double angle expansion. So this is going to give me k times 2 sine x cos x all over sine x, and you'll find that your sine x's cancel, so you end up with 2k cos x. All right, so that's how we proved part 3.2. SQ is equal to 2k cos x. We did that by simply working in triangle PSQ, and we worked with the information that we were given there. Okay, now 3.3 says, hence proved that SQ is equal to 6 cos x over tan y. So hence is a big clue that you need to use what you've already done. So what have we just done? Well, in part 3.2, we've just proved that SQ is equal to 2k cos x. Again, we did that by working with one of the triangles in the cyclic quad. Now, if you look at what they want you to prove, SQ 6 cos x over tan y, how do we approach that? Well, what I would do is I would compare this to what we've done in the previous question, and I see immediately that what's missing is this k. So that tells me straight away that I need to get rid of this k, and I need to find the value of k so that I can then make a substitution and get what they want. Okay. Maths is all about logic. We reason it out. All right. No k, therefore I need to get rid of the k. How do I get rid of the k? Well, if you look at triangle TPQ, all right, k is a side in that triangle. So I can use triangle TPQ to work out a value for k. All right? I've got a 90-degree triangle. So I'm going to say in triangle TPQ, what do I have? I'm looking for the adjacent side. I'm given that the opposite side is 3. So I can say tan of angle y is equal to opposite over adjacent. So it's equal to 3 over k. Cross multiplying, I'm going to get that k is equal to 3 divided by tan y. Okay, so k is equal to 3 times 3 divided by tan y. So that bit of information we're now going to use and substitute, because remember we've just shown before SQ is equal to 2k cos x. Our whole aim with me trying to work in another triangle was to get rid of k, and what we've just shown is that k was in fact 3 divided by tan y. So I've just proved that to you when we went to the top of the screen, so I can replace k with 3 over tan y, and that's times cos x. So I end up with 6 cos x all over tan y. All right, which is nice because that is exactly what they wanted you to show. All right, brilliant. So let's check over with John, and he'll tell us if we've got time to do another question or maybe take one of your guys' questions.
Okay, Natasha, we've got a few minutes. I don't know whether we're going to get a full question in. I just wanted to let you know that, and I hope I get this right, Sina Temba gives a shout out and says, thank you so much, Natasha. She did question number 2.2 all on her own, and she's checked her answer, and she wants to thank you. She got it right.
Yay, well done.
So you guys, you see, the thing is that if you do it beforehand, and you follow, it makes so much more sense. There was a question from Swana Lawando, who wants us just to check what the proof was for D3 and D4 equal to 90 degrees. I know it's a few questions back, but...
Okay, so we'll use this diagram and we'll just do it on D3. Okay, it's quite a quick one, John, so we'll just have a look on this diagram, mindsetters. You want to know why D3 plus D4 is 90? Well, we've already established that MD is the center, is the radius, and that's because M was given as the center of the circle. That's your starting point. So MD is a radius. Also, in the given information, they actually tell you that EDC is a tangent. So we needed that information. They tell you that EDC is a tangent. You know that MD is the radius because M was the center of the circle. And then there's a theorem in maths that says the radius is perpendicular to the tangent at the point of contact. So that really, that's conclusion that I got to there, that was 90 degrees. It comes straight from a theorem that you guys are expected to know for your exams.
Natasha, have you got any tips about learning those theorems? I know that there are some that are examinable, and we're expecting some of the theorems to actually come up as questions in the final exam. Isn't that right?
Yes, absolutely. Guys, please make sure you go through your theorems. You need to learn them. You can be asked to prove your theorems. We can't can't tell you which one. So you need to learn all of those that you are expected to learn. And John, what I'd actually like to mention here is that the nice shows that we've also put on with similarity and this Euclidean geometry for the mindsetters, where we go through how you should state a theorem and what the reasoning is. It's quite a nice thing for you guys to pay attention to. It was on in the previous show before we did this live one. So if they can, get the notes for that and go through that. It is very important information, and so I don't want to rehash that whole show, but I do want to tell you guys that you need to know all of the theorems that your teachers tell you you expect to know. You can be examined on any one of them, but you need to know the conclusion of what every theorem says. So you need to know exactly what the statements are from every single theorem.
Have we got time for that last trig question? Do you think that...
Okay, so I think let's have a look, John. Let's see how far we can get. Maybe I can do the most important part, because I know that the part that you guys struggle with is just the beginning part. So let's just try and get that done. And that, I think, could be quite helpful. So this is a general solution question, question 4. They ask you to determine the general solution. What I want to do here, the way I can help you the most, because people look at this, once you get to the solving part, it's easy. How do you get to the solving part? Okay, so I look at this and I see, well, I've got sine squareds and I've got sine and I've got a cos. The cos is out of place. So straight away for me, I want to change cos 2 theta to its expansion, which is 1 minus 2 sine squared theta. All right, so that's your starting point. Plus 4 sine squared theta minus 5 sine theta minus 4 is equal to 0. Okay, now I can work with this. Everything is in terms of sine. 4 sine squared minus 2 sine squared is going to give me 2 sine squared theta. All right, minus 5 sine theta. I just bring down the middle term, and then 1 minus 4 gives me minus 3. Guys, really, once you've gotten to this part, it's really now just trying to solve a trinomial, and it no longer from then becomes tricky, because all you're going to do is factorize that trinomial and then solve for theta. So we factorize that, and I really think this is going to help you guys quite a bit if you did struggle with this question. You factorize that trinomial into 2 sine theta, and we've got sine theta. We're going to get 2 sine theta plus 1 and sine theta minus 3. Let me quickly check that. Yep, that is correct. So you get 2 sine theta plus 1 times sine theta minus 3 is equal to 0. Once you get to that part, really, this question is done.
It's like just factorizing
Yes.
a quadratic almost.
Absolutely.
And just doing a normal solution. Yeah, great. Thanks, Natasha.
Pleasure.
I think we've pushed it right until the last minute. We've got a few more seconds left. Guys, thank you so much for joining us, and I hope that you've benefited from this. Remember that there are some more programs coming up after this live show, so don't forget that. There are other things happening. Stay on the page, get the links, download the notes, and we're not going far away. Want to remember that coming up after the spring school holiday, there will be more programming for maths. We'll be going over prelims, so stay connected. There's lots happening on the page. For the last thing, please go to the page and be a bright spark. Enter that competition, and you could be an amazing winner. From me, Natasha, and John here in studio, thank you. Goodbye.